In this video, I'm going to demonstrate the use of the Stata program in carrying out a binary logistic regression. Binary logistic regression is carried out in those cases where you have a dependent variable that is dichotomous with the levels representing group membership. And the basic idea is that you are attempting to predict group membership as a function of a set of predictor variables. So in this particular data set that I have open right now, I have a set of variables, and one of them is going to be the dependent measure, which is the donate variable. So the data or the analysis is essentially going to be aimed at predicting participants' intentions to donate to a political cause or not to donate to a political cause. So the donate variable is actually coded 0 for intent not to donate, 1 being intention to donate. And then we're also going to look to see whether donation intentions are as a function of a set of predictors. So if we take a look in the data editor, you can see that we have the donate variable coded 0 for intend not to donate, 1 for intend to donate. For gender, we have codes of 0 for male, 1 for female, and then we have political interest, dogmatism, political efficacy, and consideration of future consequences. And these variables are all essentially treated as continuous. So to carry out a basic logistic regression using the menu option, we'll go to Statistics, Binary Outcomes, and go to Logistic Regression. We actually have a couple of options. I'm just going to stick with this one for the time being. We'll click on Dependent Variable and Donate. So that's our outcome variable. And like I said, we have the value of 0 stands for or represents intention not to donate. A value of 1 represents an intention to donate. Now, it is important to note too that in the context of logistic regression, we generally are focusing in on the probability of membership in a target category. So we have to think about one category is reflecting a baseline or reference category, the other representing a target category. So it's very much akin to our standard notions of dummy coding, where when we are applying dummy coded variables, one level will serve as a reference or a baseline group, the other one representing a target group. So at any rate, we'll go to independent variables, we'll select political interest, dogmatism, and gender. By virtue of it being dummy coded with only 2 levels, we can include that and treat it as a scale variable, even though it's technically a nominal variable. If we happen to have a variable that is nominal or ordinal with more than 2 levels, then we might choose to treat it as a factor. And so there are other ways of doing that through the program. Either that or just creating a set of dummy variables, and we could still run it through this option. So I'm going to click on OK. And so we have the basic model. And so in evaluating the model, there are 2 levels really that we want to pay attention to. We want to look at the overall fit of the model to the data, and then also if the overall fit looks good, then we want to look at the individual predictors in the model. So you'll notice that up here we have what's called the likelihood ratio chi-square test. And essentially, this test is testing whether the model that contains our full slate of predictors represents a significant improvement in fit over a null model with no predictors. So if this test is statistically significant, then that would indicate that we have evidence of a good model fit, or at least in relation to a null model. And so we have the chi-square statistic or test statistic, and then we also have the p-value right here. And you can see that the p-value is less than our conventional 0.05 threshold. So we would essentially we would reject the null that the baseline and our full model exhibit equivalent fit, and essentially conclude that our current model exhibits a significant improvement in fit over the baseline or null model. Now, we also have the Pseudo Rsquare And this is basically the McFadden's R-square. And what this is an analogy to the least squares R-square. So it's not computed in the same way, and it really doesn't mean exactly the same thing. So we sort of use it as like I said, kind of an analogy to the R-square that we have in least squares regression. But this is certainly not a proportion measure in the same sense. It doesn't represent the proportion of variation in the dependent variable accounted for by the predictors. It's essentially an analogy. It's a little bit tricky to interpret, but that's what this is. So we're going to mainly focus in on just saying that it looks like our current model exhibits a significant improvement in fit over a null model, and look at the individual predictors. So you'll notice we got political interest, dogmatism, and gender as predictor variables. And so we have our table, our regression coefficients in this column, standard errors, and z values or z-scores that are computed as a ratio of the regression coefficients to the standard errors. And then we also have our p-values. And so we would interpret these pretty much the same way that we do in the standard least squares regression, where, for instance, a p-value equal to or less than 0.05 would be judged as statistically significant for the predictor. A value that is greater than 0.05 would be an indication that the predictor is not significant in the model. So just to kind of unpack things a little bit, keep in mind that basically these coefficients in least squares regression, the regression coefficient can be interpreted as the amount of change in the dependent variable as a function of 1 unit increase on the predictor variable. So in other words, the unstandardized coefficient is capturing the predicted change in raw score units for every one on the dependent variable for every 1 raw score unit increase on the predictor. In the context of logistic regression, it's interpreted a little bit differently. It's the same basic idea, but in this case, what we're looking at is predicted change in something called the log odds. And what this is pertaining to is really the predicted probability of group membership or membership in the target group. So we have to think about it in this kind of way that we can, our model, we're essentially trying to kind of model the predicted likelihood or probability of falling into our target group. So essentially what we're doing though in capturing that is we are actually forming a ratio of 2 probabilities. So we have essentially probability of A, which is membership in the target group, over probability of B, which is membership in the non-target group. And this is what is referred to as odds. So essentially, if you ever hear the term odds, it's just simply a ratio of probabilities. The probability that one event will occur versus over the probability that another event will occur, assuming that these 2 events are mutually exclusive. So in the context of logistic regression, we only have 2 groups. So A is literally going to be the probability of falling into the target category, or in our case, the intention to donate category, whereas B is essentially the probability of falling into the non-target category, or the intention not to donate group. So essentially what's happening though is that we are taking our odds and then obtaining the natural log of those odds. And so that's what this is really reflecting, is the change in the log odds, or predicted change in log odds for every 1 unit increase on the predictor variable. Now you may be asking yourself, why all of this? Why not just model the predictive relationship between these variables here and predicted probabilities? And the reason why is that the relationship between our predictors and predicted and probability values is nonlinear. And in the context of logistic regression, we can just kind of look at it as we start introducing the concept of a logistic curve, where we're looking at probabilities of falling into our 2 groups. And so And so, the relationship between our predictors and our dependent variable is nonlinear. And so we essentially modeled the relationship between our predictors and our outcome variable through this process of essentially converting our probabilities to odds and then to log odds. So that's all that's happening. So it may be kind of confusing, but just keep in mind that's essentially what's going on. So I do want to note too that when we look at odds, if the probability of the target event is equal to the probability of the non-target event, then what we would expect is the odds will equal 1. And so if the probability of the target event is greater than the probability of the non-target event, then we would be looking at an odds greater than 1. And obviously, if the odds of the target event is less than the probability of the target event is less than the probability of the non-target event, then we'd be looking at odds that are less than 1. So we want to just kind of keep that in mind as we sort of move forward. So at any rate, so even though that we're talking about these coefficients in terms of log odds, you can still loosely think about it as the relationship between the variables and the predicted probabilities with respect to target group membership. So because obviously if the odds are greater than 1, then that's going to indicate that a greater likelihood for event A or membership in the target group as opposed to the non-target group. And so a positive value actually on this is going to be telling us very much the same thing. So you can see that we could say that political interest is positively related to the likelihood of falling into the intention to donate group. So basically, at higher levels of political interest, you would expect a greater likelihood that a person would fall into the intention to donate group. Whereas at lower levels of political interest, you would expect less probability of falling into the intention to donate group. Dogmatism is a positive value here, and that's going to also indicate that folks that tended to be higher in dogmatism also expressed would be more likely to express an intention to donate, whereas those lower in dogmatism might be would be less likely to express an intention to donate. Nevertheless, the first predictor was significant. The second one was not, if we use a two-tail criteria. The fact is that I kind of expected this to be positive anyway, and so if I was adopting a one-tail criteria, that would be considered statistically significant. The negative coefficient right here, if we remember our coding, 0 for male, 1 for female. So the fact that this is a negative coefficient would indicate that males were more, the probability of falling into the intention group was higher among males than among females. But that difference really was not statistically significant in the model. So, just kind of keep in mind that basically, as you're looking at these coefficients right here, just think about it this way, that basically a positive coefficient is basically indicating a positive relationship between the predictor and the likelihoods of falling into the target group. A negative value would indicate that at higher levels of the predictor, the likelihood of falling into the target group is lower. So that's kind of the way to think about it. It's not technically, like I said, we're not expressing that likelihood in the form of probabilities, but rather we're kind of capturing that through the vehicle of log odds. So, kind of moving on, let's say that we wish to look at the the odds ratios. Well, we could certainly do that in a couple ways. If we go back through this original option here, we can click on report odds ratios, and we'll get those. You can see right here that in our output we've got odds ratios, which again, when we think about odds, we're looking at a ratio, essentially a ratio of probabilities. Probability of falling into the target group over the probability of falling into the non-target group. Now, the odds ratio that you see right here is not this. This is actually, the odds ratio is actually reflecting the changes in odds for every unit increase on the predictor variable. And so this is actually reflecting a ratio of odds. So, for instance, if we started at the mean on political interest, we would expect a certain odds at the mean on political interest. And, let's say we increased our political interest by 1 unit, then we would expect the odds to be multiplied by this factor right here to produce an odds at 1 unit above the mean on political interest. So the odds ratio is reflecting the changes in odds for every increment on the predictor variable. So that's the way to think about that. And you'll notice that when we look at our original table right here, you've got the coefficients and then you've got a confidence interval. And basically, what we're testing right here in terms of the null hypothesis, the null is pretty much the same as it is in the context of least squares regression, the null being that the regression coefficient in the population is equal to 0. And so if we were using the 95% confidence interval, using the original regression coefficients, and we're looking to see if the null value of 0, does that fall within the interval or does it fall outside? So, you can see that 0 falls, outside of this interval right here. So it's actually falling, down on this end. Whereas 0 is falling within this interval here, and it's falling within this interval here. So if we were assuming a two-tailed test for each of those predictors, only one of them would have been significant, that being political interest. We also have a confidence interval for the odds ratio. And so what we're looking for is essentially the null hypothesis is that the odds ratio is equal to 1. So that's the null hypothesis. So if 1 falls outside of this interval here, then we would reject the null. If it falls between the lower and the upper bound of the confidence interval, then we would maintain. And so you can see 1 falls between these two values here and between these two values here. So again, that's indicating that we would be maintaining the null with respect to the dogmatism and gender variables, again, if we're assuming a two-tailed test. Now, we also have some post-estimation options. If we go to post-estimation and click on specification, diagnostic, and goodness of fit analysis, we'll start by just looking at goodness of fit test. So I'm going to double-click on this and go to the Hosmer-Lemichaud goodness of fit test. So basically, this is another sort of global measure of fit, and this is a chi-square test, and it's been pretty roundly criticized, but it's still information that you could use perhaps. So I'm going to click on that, and what we have right here is the Hosmer-Lemichaud test. It's a chi-square test, and this is a p-value. And now, unlike the chi-square test above, where we were looking for significance as an indicator of good model fit, at least relative to the baseline model, here we're looking for non-significant chi-square test. So non-significance with the Hosmer-Lemichaud test would be an indicator of good model fit. And so in this case, it's the chi-square test. The chi-square value is 8.11, and the p-value is 0.4229. So it's indicating a good model fit to the data. Another bit of information that you might ask for is the classification table and sensitivity tests and so forth. But I'm going to click on that, and what you'll see right here is a little table that's giving you classification results. So based on what we're doing in our model is we're generating predicted probabilities for group membership. And then based on those predicted probabilities, we can essentially generate a prediction as to whether a person would fall into group 0, the intend not to donate group, and the group 1, the intend to donate group. So the classification table is really essentially looking at the correspondence between the observed group membership and group membership that's predicted based on the model. And so you can see right here that you've got true and classified. So this is reflecting the observed group memberships and then memberships based on the classification or based on the prediction model. So you can see that in this case, we had 41 cases that were observed to fall into the intention to donate group, whereas we had 134 cases that fell into the do not intend to donate group. Now, of the 41 that expressed an intention to donate, we had 12 of those 41 that were predicted correctly by the model to fall into that category. So, this is the positive values really reflecting the group that's coded 1 right here, and so that's the intention to donate group. So when we look at the rate, the accuracy rate for that group, you can see it's about 29%. So it's pretty darn low. It's not doing a very good job. The model's not doing a very good job in terms of predicting those individuals who would express an intention to donate. Now over here, you can see that 129 people were predicted by the model to express an intention not to donate. So we had 129 out of 134 that were correctly classified based on the model. And so you can see we had an accuracy rate of about 96% right here. So you can see that overall, the overall accuracy rate was about roughly 81%. But we do a really horrible job of predicting who expresses an intention to donate versus predicting those who express the intention not to donate. So, you can use this information right here as some more information when it comes to making a judgment about the fit of the model. Now, I do want to note too that you also have you can also use syntax in order to run these models. And the nice thing about Stata is that actually if you run your models through the syntax options, you do get, you actually get the syntax for each of them. So you can see right here it says logit and then the names of these variables right here. And so that's essentially the commands for generating a logistic regression. So if you can start to kind of learn some of the syntax, it can be a little bit quicker and offer a little bit more flexibility when it comes to testing models than just running it through the menu. So just to kind of highlight this, I'm just going to copy this and put it down in the command line and then enter. And so there you go. There's the analysis. So basically, you're following the same general idea as you would with least squares regression. You have the regression command, which in this case is logit. You follow it up with the dependent variable name and then the names of the predictors. And so there you go. If you want to look at that odds, if you wanted the odds ratio, it just basically involves a modification of this part of the statement right here with a little comma and an OR. So if I'll just, paste that down here and you can see that's it right there. So there are odds ratios. To get the goodness of fit test for the Hosmer-Lehmann show, you want to be sure that you would be typing in estat GOF comma and then group 10 and then basically in the parenthesis, and there you go. So that's the nice thing about knowing a little bit about the syntax is you can kind of do things a little bit quicker than just sometimes running it through the menu. And then to get the classification table, it's just estat classification. Now I do want to show you another example. This is using a do file that I've created, and so I've got the syntax for essentially what we just generated. It's all of this stuff right here minus the odds ratios. And so what I want to do is, let's say that I wish to test sort of a hierarchical or test the predictors in a hierarchical sense. So let's say I want to do kind of a hierarchical logistic regression where I want to add have a set of predictor variables at one level and then add in another predictor or multiple predictors in a separate model. So so what I'm what I'm doing right here is I have the basic model, everything, and then what I'm going to do is I'm going to have a second model where I'm going to add in CFC as an additional predictor. So in this model we don't have CFC, in this one we do, and so we're going to see if essentially is there a significant increase in fit as a result of adding in CFC. So in this case, what we're going to use is the estimates command. We're going to store, it says estimates, store, and then ML. And so what that's going to do is it's going to store the chi-square value and whatever estimates from the first model. And then I'm going to do the same thing for this second model. So, and I'm going to run this kind of as a batch instead of running this separately. But so once I've stored the estimates from both models, then I can use the LR test, which is the likelihood ratio test, to test the difference between model 1 and model 2 and sort of see if, do we improve, is there value added in adding in the predictor if I want to do this kind of in a hierarchical way. So I'm going to highlight all of this and click on this little button right here for execute selection. And so now I've run the analysis. And so you can see right here, this was our original model. And so we've done that. I've generated the classification statistics, the Hosmer-Levy show, and then estimates store. So I've stored the estimates from model 1. Then we have essentially the next model where we've added in CFC. And when we've done that, now you can see CFC in this case right here, there's actually a negative coefficient. It's not statistically significant. So you can see right there, really just adding that in didn't really help us out all that much. We have the classification statistics related to that. You can see that essentially we have a not much of a gain in terms of predicting who intended to or who was going to express an intention to vote, or not vote, to donate. So really not much of a change in the overall classification accuracy or anything like that. There's a goodness of fit test, and then so you can see right down here the likelihood ratio test where we were basically we had model 1 versus model 2, and so you can see that that there was no significant difference in models. So basically adding in the additional variable for model 2 didn't yield a significant improvement in fit. So that's kind of a quick and dirty overview of binary logistic regression using Stata. There are other options that are available. If you want to do things like use robust standard errors or bootstrapping or things like that, you can certainly do that. This was just, like I said, sort of a quick overview. So I hope that you find this helpful.